Okay, everybody. So what we're going to be looking at today is section not 5.5, but 10.4 and 10.5. Really, what we're looking at is 10.5, and we're only going to give you a tiny bit of 10.4 that you need in order to understand what we're doing in 10.5. All right, so let's go ahead and get started. So the main topic is Euler paths and Euler circuits. Okay, but to understand what an Euler path and an Euler circuit is, you need to understand what a path and a circuit is. So I've got some definitions down here. Here they are. Definition two, definition one, that kind of thing. I'm gonna just scroll past them and I'm just gonna write down some stuff. So let me get a new page here. That did not do it. How do I do it? Hold on. You have to write, and then I can scroll. Yes, magic. Okay, so let us talk about these definitions then. I can come up here. Let me grab the definition. I will steal it. Copy. Come down here. Paste. Hey, make it big. Okay. So this is the definition from the previous page. And so what this is about paths and circuits or cycles in a graph. So it's a pretty simple concept. We don't really need to pay too much attention to this definition here. So let me just, that's not what I want. There we go. So let me just draw a graph here with a bunch of vertices. Let's give them names: A, B, C, D, E, F, G. And we need some edges on this graph. So let's put some edges in. All right. So we'll put a couple more. Okay, good enough. So there's a graph, and we could call that graph graph G. Okay. So basically, what path is so it says up here a path is a sequence of edges. Okay. Basically going from one vertex to another vertex. A starting vertex. So it takes you from a starting vertex. Let's just call it, what do they call it? X0 to ending vertex. Oops. X in. Okay. And then we say that the path has length in. Okay. So for example, if I go to this graph here, if I start to A, or start to A, that doesn't make sense. As an example, we're just going to have a path from, let's say, A to F. So I'm just going to draw a path from vertex A to F, and vertex A to vertex F, and I want to know what the length is. What is the length? Okay, so I'm just going to draw a path. There's more than one, but basically if you start at A and you head to B because we don't have any choices, and we're trying to get to F eventually, but we don't have to take the fastest way or anything like that. So I could go, for example, I could go, what do I want to do? I can go from A to B, B to D, D to E, E to F. That could be a path. Okay. And so technically the path is the edges, not the vertices, right? So technically, if I give the edges names like E1, E2, E3, um, E4, I should have done this in another color. I'm going to, hold on. Let's take blue. E1, E2, probably the numbering's different. E3, E4, E5, E6, E7, E8. So I've got a bunch of edges on here. And so the path is technically this. A path from A to F is, and it's a sequence of edges. So we're just listing the edges that we traveled along. So we traveled along E1, then E2, then E5, then E8. So 1, 2, 5, 8. So E1, E2, E5, E8. That's the path. Okay. Now, having written this path here, um, because there are no multiple edges, we could have just listed the vertices that we traveled to. We can just list the vertices we traveled along. Instead, because there are no multiple edges, which in this case means there's no difference between the edges. There's only one edge between each vertex. There's only one edge between each pair of vertices, actually. So technically we have the path up here, but we could have just listed it like this instead. Like vertices. So what vertices did we take? Well, we could just list them. Hold on, make smaller. We started at A to B to D to E to F. So I could have said A, B, D, E, F. Right, so that would have worked as well. The only thing you have to be aware of is in terms of counting, and that is the length. The path has length n when you go from vertex x0 to xn, which means that, like, if you think of the numbering on here, like x0, x1, x2, x3, x4, there's actually 5 vertices here, but it was only 4 edges, and the length of the path is the number of edges, not the number of vertices, right? So this is 1, 2, 3, 4, length 4. Okay, I should even have said that up here. So a sequence of edges of n edges that takes you from starting vertex x0 to ending vertex xn. The path has length n. Okay, so that's why I added this second question here, was just to make that clear. So like we could say, so there's our path listed 2 different ways, and we could say the path is length 4, which is the number of edges, or 1 less than the number of vertices here. Okay, so that's what a path is. A circuit, next thing we want to talk about, which is also defined up here, but again, we're not going to read this because it's too complicated. A circuit, oops, is just a path that ends, well, starts on and ends at the same vertex. Okay, so again, let's just draw a graph. Oops. So I'm just drawing a path here. Sorry, I'm just drawing a graph here. Um, and let me add a couple more. Okay, good enough. One more. Okay, so let's call that H. And so all it is so a circuit. If I give these all of the edges should have names again. So E1, E2, E3, um, E4, E5, E6, E7, E8, E9, E10, E11, E12. That's a lot of edges. So let me. I'm only going to name one vertex. We can call that A. So a cycle um, in this graph in H is, and again, it's a path, which means it's a list of edges, not a list of vertices, technically. So let's just draw one here. So we're going to go from A to A. So let's start at A. We can go E1 to get over here. And then from E1, maybe we'll go E9. And then E9, we're going to go E10. Then over to E11. And then let's head back on E5. Okay. And I end up back where I start. So it might be, what did we do? We went here first. So we went E1, then E9, and then E10. E9, E10. Let's move these. So 1, 9, 10, 11, 5. There you go. Okay, so there's a cycle. And that's if you list it as edges. And if you wanted to list vertices, we would actually have to give all these vertices names, which I don't want to do. So I'm not going to. But that's it. So you trace this around. We just went around the graph and we ended up back at A. So it started and stops at vertex A. And that's what makes it a circuit, is that it is stopping where it started. Okay. Then the last definition that we had in that little definition box is a simple path or circuit is a path or circuit that does not reuse any edges. Right. So all of the edges were not reused here. I only went on E1 once, E8 once, E11 once, E10 once. I just got lost. E1, E9, E10, E11, E5. Okay. We didn't reuse any of them, right? There's no E1 and then another E1 and then another E1, nothing like that. All right. And that's what it means to be simple, is that does not reuse any edges. So let's go back up here and see if we can get through some of this set of notes. Okay. Wait, why? I don't know what happened to these notes. That has nothing to do with what we're doing. Okay, let's actually talk about what we do want to do, which is the problem of Euler paths and circuits. So we were just talking about paths and circuits because specifically I wanted to talk about Euler paths and circuits. Okay. And what an Euler path or an Euler circuit is going to be a path or a circuit that uses all of the edges in the graph. So if you read these here, can we travel along the edges of a graph, starting at a vertex, returning to it by traversing each edge of the graph exactly once? So this is just going to be, uh, yeah, use all edges in a circuit, I think. Yeah. Um, why do I keep putting an E on the end of circuit? That's weird. Use all edges in a circuit. And the other question here is, can we travel along the edges of a graph starting at a vertex and return to it by visiting each vertex of the graph exactly once? That's, a slightly different problem, but yeah, it's a slightly different problem. So this is just going to be a circuit, visit each vertex in a circuit. Okay. And we know what circuits are, so those make sense. Okay. So here is a problem that this was originally proposed to solve. Um, so we've got a town, I think that's Königsberg, something like that. I think there's an R sound on that O with the accent thing on it. Doesn't really matter. Um, but Königsberg bridge problem is what this is called. And so the idea is this. So you have this town and it's got a river. So this is a river, not a, you know, walking path, right? You don't go on there. Right. So that's water. Okay. And we got these bridges over the water. And the idea is um, we wanted to know if you can go through all of the bridges and get back to where you started, but you can't cross the bridge more than once. Okay. So that's what we're talking about here. We've got this problem written down. They wondered whether it was possible to start at some location, travel across all of the bridges once without crossing any bridge twice, and return to the starting point. Right. So that's actually like one of these problems up here. Um, a circuit that uses all the edges and a circuit that uses all the vertices. Um, which is it? Well, we'll have to see how we're going to solve this problem. Okay, so this is called the Königsberg bridge problem, and that's what it is. Can you cross all of these and cross each bridge once and return to the starting point? And you can try it out and just see how it goes. It's not that hard to try. You just pick a starting point. Like, let's say, okay, we're going to start here. Okay. So if you try to take the bridges, you say, okay, we're going to go here, and then we're going to go here, and then here, then here, then that one, then that one, and now we're stuck because we didn't use this bridge over here, and we can't now because we're on the wrong side because we can't go back across a bridge. So we did not succeed. So you say, okay, well, we didn't do it that time, but maybe we can do it again if we start in a better way. Like maybe we just need to start here. And maybe we'll get this bridge first and then we won't be left over at the end. So let's go here and then here. Um, oops. Then here. Why stop that? Just want to get here and then here. And okay, we can't do that. That gets us stuck right away because we have no way to get back across. You can't go around because that's crossing the river, and there's no bridge over here. All right, so that didn't work. Try again. Maybe we go here, 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 here. Okay, we're back in the middle. We're stuck again. We didn't use this bridge. um, you could keep trying to solve it, and it doesn't look like it's solvable. So we try it, and I don't see a solution right away. Okay, but just because I don't see a solution, that doesn't mean it's not solvable. It just could mean that I'm bad at this. So we try it again. So his solution, um, yeah. So his solution is the first to use graph theory, and he used a multigraph to represent this problem. So here's how we're going to solve this with a graph. Okay. So what you do is we're simply going to do this. So we want uh, each piece of land is a vertex in the graph. Okay. Each bridge is an edge in the graph. Okay. And so if you know that, and we try to draw this as a graph, what you would do is you see how these pieces of land are numbered, not numbered, those are called letters, not numbers. Um, each one of them is lettered. And so you have C, A, B, and D. So A, B, C, no, A, B, C, D. So four of them, right? So if you're trying to make a graph, just copy it as well as you can. So like I've got C on top, then A, then B. Those are different pieces of land, and land are vertices. So if I'm trying to draw this, I would draw it as C on top, then A. I should use uppercase like they did. A, that's not A, that was supposed to be C. C, and then A, then B on the bottom. And then over here, you've got D, right? C, A, B, D, C, A, B, D. So each piece of land is a vertex, and then each bridge is an edge. So what you do is you just say, okay, like from A to C, there's a bridge and then another bridge. So there's two bridges that go from A to C. So you go one bridge, two bridge, like that. And then there's two bridges from A to B, bridge, bridge. So two bridges means two edges, edge, edge. Okay, that's not done. We've got a bridge here, which is from D to C, right? All of this up here is C. So we have a bridge from D to C. That. We have a bridge from A to D, like that. And then we have this bridge, which is from D to B. There you go. So there is your graph representation of this problem. Okay. And so here's the graph, that they drew. And then we can actually talk about an Euler circuit, because that's what we're going to be solving this problem with. So the definition is down here, but I'll say it up here. An Euler circuit is a simple circuit. Did they say that? Yes. Simple circuit that contains all of the edges in the graph. Contains or uses all of the edges in the graph one time. Okay, so we just use all of the edges. So it's still the same problem, right? Like if you try to find the Euler circuit on here, Like I can start at C, you go C to D, D to B. I can take the left path here. Um, and now I'm stuck because if I go up to C like this, I didn't use this edge or this edge, so that didn't work. If I come back on this, now I'm stuck over here. There's no way to use either of these. Uh, if I go over here, I'm stuck at D, and I didn't use any of these. So, again, it's the same problem, so it's not any easier to solve now. But an Euler circuit is a simple circuit that contains all the edges in the graph. And then our problem is the bridge problem. Is actually, does the graph contain an Euler circuit? Okay, so yeah, why is it called an Euler circuit? Because if you scroll up and read the part that I didn't read, the Swiss mathematician Leonhard Euler solved this problem, right? So Euler solved it, so it's named after Euler. There you go. So now here's the definition of an Euler circuit. It says what we just said: simple circuit containing every edge. An Euler path is a simple path containing every edge, right? So there's an Euler circuit and an Euler path. So the circuit starts and stops at the same vertex, and a path is a path containing every edge. Oh, actually, so to back this up, technically, I don't think the problem up here said that we needed to. Oh, yeah, I did. Never mind. Return to the starting point. So it was a circuit. For a second there, I thought it was a path. Okay, so the only difference between a circuit and a path, remember, is that circuit, you have to end up where you start. And for a path, you could end up on a different vertex. Okay, so let's just try to find an Euler circuit on each of these. So I'm going to copy these twice because we're going to try to find an Euler circuit and then we're going to try to find an Euler path. Let's take that, copy, paste. She would have just pasted it the same size, but okay. So let's try to do this. So we're going to try to find a circuit. Oh, okay. I guess we don't need it twice. We don't need that twice. So we're going to look for circuit first and then try to find a path. So circuit means we stop where we start. Let me find this. Let me do this. Okay. So let's just try to find it. So like if you're here and if you try to find an Euler circuit, that means we're trying to use all the edges. So we go here to here, 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 here to here. Yeah, we did it. We remember that the definition is talking about edges, not vertices. So even though we visit the vertex E twice here, that doesn't matter because we use each edge once. So we just used this edge first, then here, then we went here, then we went here, then we went here, then we went here. Right? So just 1, 2, 3, 4, 5, 6. Right? And we started and we stopped here. So we found a circuit, which is also a path. Right? Because a circuit and a path are the same thing. It's just a circuit ends up where you started and a path doesn't. Okay, let's try to do the same thing on the next one. Again, we'll start at A. So let's go A to B. This already looks bad, right? I can go A to B, B to C. The problem is going to be that like whenever I go to the center, like now, then if I can't ever take this path, right? Because if I go from E to B, I'm stuck at B with no way to leave. But if I don't go to B, like if I go to D, then how will I ever get back here? I don't know. Actually, it's straight. We go here, we go here, and we go here. But I missed this one. So that didn't work. Right. So you can try it yourself and see how far you get. Um, maybe you think, okay, well, I'm just going to stop. I'm going to start here. And, maybe that works better. Let's see. Go here, 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 here. Got the same problem, right? If I go back this way, then I can never leave. So if I go up, then I go over, I just end up stuck, right? It doesn't look like there is one. So no path or circuit. I was looking for a circuit, but there's no path or circuit. Okay, let's try the third one. This one, I don't know if you can do. Again, let's try to start at A. Why not? Okay, so let's see if we can do this. So let's go A to B, to D, back to A, over to C, over to D, over to E, over to B. All right, so it looks like we did it, right? So what order did we do it? Try to remember. Well, it doesn't really matter. I don't remember either. Okay, so let's go there, 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 down to C, over to D, over to E, back up to B. And that's, there you go. So I just numbered it. So we started here and we went 1, 2, 3, 4, 5, 6, 7. Okay. There we go. That is an Euler path. And the reason it's not a path, right, was we ended up here. So we started at A and we ended up at B. Now you can keep trying this to see if you can start at a different vertex maybe and then go around in a circle and end up back to where you started, but you won't be able to. So, sometimes there's circuits and paths. Sometimes there's a path but no circuit, and sometimes there's neither. And that's just how it is. So, yeah, that's just how it is. Yeah, you can do the same thing for directed graphs. We're not really going to pay attention to these or anything, but um, like if you start at A, go to B, okay, you're stuck. So we didn't do it. No path or circuit. I mean, you can keep trying, but I don't think you're going to be able to do it. You could have gone here to here. Oops. You could have gone here to here, over to here, up here, but then no way to get back because we're following the directions of the arrows. Try here. A to C, to B, to G, to D, to F, back to A. Hey, look, that worked. So that was a circuit, which means path as well, because a circuit is a path. 1, 2, 3, 4, 5, 6, 7. Okay, last one. C, D, B, C, A, B. Oh, that was a path. Okay, so what did we do? We did it here, then we had to go here, then we had to go here, and then we had to go here. And that was a path, but not a circuit. Okay, so I mean, I hope you get the point. We're trying to use all the edges. Sometimes we can, sometimes we can't. You're trying to get back to where you start, but sometimes you can and sometimes you can't. So what does it say here? We can find Euler paths and circuits for small graphs relatively easily. What about large graphs where you can't do this by hand? So what we want is a theorem. Okay. And here's the idea. So I'll just read it. When you make an Euler circuit, you must enter each vertex on a certain edge, and then you need to be able to leave the vertex on a different edge. That's always what you do, right? So when we have a problem like we do here, right? Let me erase this. So the problem is always this, right? Like if I start here and then I go, oops, I don't know why it does this. If I go here and then I go here and then I go here, this is the problem. The problem is I can never go back to E. Sorry, I can never go from E to B, because if I go from E to B, there's no edge to leave on, right? So if there was an extra edge from here going, somewhere else, like if there was an edge like this, then I'd be fine, because I could go, why? Because I could go to B and then I could leave B on this extra edge. But I can't leave on this extra edge if there is no extra edge, right? So that's the problem. So whenever you go to a vertex, you need to be able to leave the vertex. And what that means is this, right? So I used one edge and then I used another edge. So that means every time you go through a vertex, like we went through vertex B, you use a pair of vertices, because you used one edge to come into B and you use one edge to leave B. So come into B, leave B. So 1 and 1. So that's 2. And the problems arise when you can't do that, right? Like I can trace it around there, but now I'm stuck at B and there's no way to leave B. So I fail. Okay. And so once you notice this idea that you have to enter each vertex on an edge and then leave the vertex on a different edge, you get the idea of what the problem is. So the problem is that the edges need to come in pairs. The edges need to come in pairs. And if you start to look at these, you'll start to notice something. If I come to these graphs again and I look at the degree of the vertex, I'm just going to write the degree. The degree of A here is 2, right? And the degree of B is 2, and the degree of E is 4, and the degree of C is 2, and the degree of D is 2. And look at all those numbers: 2, 2, 2, 2, 4, right? And they're all even, which the fact that they're even means when you come into B, you have a way to leave, because you use one edge and one edge. And the degree is 2, so you can do that, 2 edges. If you look at the degrees on this one, 3, that's a bad way to write 3, 3, 3, 4, 3, 3. Odd numbers. And the odd numbers are the problem, right? Like we came into B and we left B, and then at some point we came back. And so we used 1 to come in to B, 1 to leave B, a third 1 to come into B, and there's no way to leave B. If the degree was 4, there'd be an extra edge, and we would be able to leave. But the degree is 3. So there is no extra edge, and we're stuck. And if you look at this case, we've got 2, 1, 2, 3, 4, 4, 2, 3, 3. So what you want to notice here is this. So the case where there was a circuit and a path, we had all even numbers for the degrees. In the case where there was no circuit or path, we had a bunch of odd numbers. 1, 2, 3, 4. Odd numbers. Bunch of odd numbers. And when there was a path but no circuit, we had, well, what did we have? We had 1, 2, 3, 4, 1, 2. We had some even numbers, 2, 4, 2, and we had some odd numbers, 3 and 3. And so these degrees here are actually telling you the story. Because in order for there to be a circuit, when you come into a vertex, there needs to be a way to leave. That means the degree has to be even. Okay? However, in a path, you can start at one vertex and end at another vertex, right? So you don't have to get back if you start at A, you don't have to get back to A if you're making a path. You only have to get back to A if you're making a circuit. So this idea that when you go to a vertex, you have to be able to leave, um, which requires an even number, applies everywhere except where you start and where you stop. So the theorem is going to tell us that they all have to be even numbers, but if two of them are odd, that's okay. If there's two of them odd, you can start at one of the odd ones and end up at the other odd one. And we didn't even have to count those up to do this the first time. So yeah, so what was the point of saying all that? Well, I'm going to erase all this. The point of saying all that was that the degrees of the vertices is what makes the problem solvable or unsolvable. Okay. And it all has to do with the fact that you have to come into a vertex on a particular edge and leave on a different edge, right? So that's the whole thing. Enter on a certain edge, leave on a different edge. That's it. All right. So let's look at our theorem here. So a connected multigraph, connected means just not in pieces like this. Right? Like this is in two different pieces. That's not connected. So connected just means in one piece. A connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices have even degree. So for a circuit, all degrees must be even. Okay. For an Euler path, two vertices are allowed to be odd. Exactly two. So they can be odd degree. Okay. And if you know that, then now you can solve the Königsberg bridge problem because we can draw the graph again, which was like this, and we had edges, edges, edge, edge, edge. I think that's how it was. And then if you write the degree next to each vertex, what you get is you end up with 3. 1, 2, 3, 4, 5. 5. 1, 2, 3. You already know it's unsolvable because we have 3 odd. And then here, this is also 3. So using our theorem that we have up here now, which tells us when you have an Euler circuit, we can say no circuit, Euler circuit, because they're not all even. And also, it wasn't the question, but there's no Euler path either. There aren't just 2 odd degree vertices. So there's no Euler path and there's no Euler circuit, which means you can't cross all the bridges and end up back where you start. And in fact, you can't cross all the bridges and end up in a different place either, uh, which you would also have found if you tried this, right? Like you go, like you try to take a path, and not only was there no circuit which would get you back to A, but there was also no way to cross this bridge. So the fact that you couldn't cross the bridge and get back to A means there's no circuit. The fact that you couldn't cross the bridge and just be over here at C or something, that means there's no path. Right. So, yeah. So the answer is no, you can't cross every bridge one time and get back to where you start. Okay. And that's Euler path thing. Now, what we're going to be doing is we are going to actually code this up. That's going to be your last programming assignment, which I should post for you soon. Um, and let's see, how long have we been talking? 46 minutes? Yeah, okay. I'll describe the algorithm very quickly here, and and then that will be it. So let me think about what I can say here. Do I want to? Um, okay. Yeah, I'll give you the idea. So let's look at this graph G here, maybe. Um, so the way this algorithm works is this. So actually, let's draw our own. Let's draw our own. It can still be the same graph basically, but I just want my own drawing. Okay. So this is, first of all, make sure that it's only going to work on a graph that meets the requirements to have an Euler circuit. Can't run this if it doesn't. And basically, what you're going to do is this. So you're going to follow these rules. So the first thing you're going to do is you're going to find a circuit. Now, how are you going to do that? It turns out to be not that hard. What you do is you just pick any vertex. So you're going to pick any vertex on here at all. So like, maybe this one. And then what you do is you just start following around the edges. And it doesn't matter which way, like which one you take, you just start taking edges. So maybe you go there, you go there, you go there, and then you go there. Okay. And then that is, I'll put like a 1 here. So that's the first thing you do is you find a circuit. Okay. And then the next thing you do is you are going to actually remove all of those edges. Okay. So you remove all these edges. Uh, okay. So you take off the part that we just looked at. And this is what you have left. Just this part. Okay. And then what you do is you're going to, while H has edges, so this is the circuit, and this is what we're calling H. We're going to go over this in detail later, but you find a subcircuit. So you're going to find a circuit in this little piece, right? We took this part away. This was a circuit. Now we're going to find a circuit here. And we're going to start a vertex in H that also is an edge, endpoint of an edge in circuit. So what that means is, like, when we broke this graph up into two pieces, they were connected right here, right? and that was this edge, or sorry, this vertex, which is also this vertex. So what you're going to be doing is you start here, and we're going to find a circuit. And again, you just start taking edges. It's guaranteed to work out, and you do that. Okay? There you go. And that's what we call the subcircuit. Okay? Then what you do is you take the subcircuit away. And what you're going to do with the subcircuit, which is this now, subcircuit. So we have the first circuit that we found, and then we have the subcircuit that we found. And then what we're going to do is we says h equals h with the edges removed. So it's not called h anymore. It's just called subcircuit. And then what you do is you take the circuit and you're going to add the subcircuit to it. And I say insert it at the appropriate vertex. So here's how this is going to look. So when I first found this circuit, like let's say that this was the first edge and this was the second edge and this was the third edge and this was the fourth edge, right? And then let's say on my subcircuit, the numbering was like this: first, second, third, right? But this vertex and this vertex were actually the same vertex. So what happens is you put them together, you put them back together like this, and your numbering does this now. So you're going to start here where we started before. You trace around the edges. So you go here and then here, but then you end up at this vertex. This was the vertex where these were connected. So once you end up here, instead of continuing around to 3 and 4, what you do is you start tracing this one around. 1, 2, 3. So you go 3, 4, 5. And then once you are back to this vertex, now you go and you finish this up, the last two edges, 3 and 4. Oops, they're not called 3 and 4, they're called 6 and 7 now. Right, so basically this circuit goes right here. So you trace this, then you trace this, and then you come back and finish it off. So you go, if we just highlight it, so you go here, then here, then here. Oops, I hate the way that works. So you go here, then here, then here, then here, then here, then here, then here. And that's your Euler circuit. Okay. Now I realize that that's kind of complicated, and we didn't talk about how we're going to code this up, but that's the idea here, right? So that's the algorithm that will do this. And of course, there's going to be lectures on the homework about how to actually code this up. And it's, kind of an interesting problem. Seems complicated, seems hard to solve on a computer, but we can do it. All right, is there anything else I want to talk about? Yeah, actually there is one more thing I want to talk about, and this will be the last thing. So this is something that's good to know for homework purposes. Good to know. You don't have to actually apply this theorem to find Euler circuits and Euler paths. Okay. What you can do is you can say there is an Euler path. On a graph. If and only if, so I'll write IFF. you can, draw the graph without lifting your pen, and tracing over edges twice. Okay, so like this right here, I'm drawing a picture. I drew that picture without lifting my pen or lifting or tracing it twice. And so I know that if I just I don't even have to put one in the center, but I did. Um, but I know that this graph here has an Euler path because I just traced it, right? I can't do it now because I don't know why, because I drew it the wrong order. What is wrong here? How did I draw it? Okay, yeah. All right, so I did it. So it has an Euler path because I can draw it. Retracing edges or lifting my pen. Now, why do we care about that? Because if you go to the homework, which I'm looking for right now, um, trying to find one. There must be one. Oh, I think it's in 10.5. Sorry, I'm just scrolling to 10.5 to find the problem for you. Blah, 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 blah. How do they say it? Yeah, there we go. Um, so they actually ask you it this way. So, example, um, Star of David, huh? Okay. I'm not going to draw it very well. So they're not. So this is 10.5, number something, 13 in the book. And the actual question is, um, can this be drawn uh, without retracing lines or lifting your pen? Right? And so the way you do it is just add vertices to the graph and then look at the degree of each vertex. And then use the theorem. So it's really easy actually, right? So like your vertices, you can add them like this, just there. Actually, you can't do that. Everywhere they intersect, you have to draw a vertex. So there, 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 there. Right? So we added all the vertices, and then you need to look at the degrees. And it's fast to look at the degrees, right? Degrees are easy to count. So like 2, 2, 2, 2, 2, 2. Those are all even. That's good. Now, what about these? We got 4. And I guess they're all 4, 4, 4, 4, 4, 4. Right? So you find all these degrees, um, all fours, and then you use the theorem. What's the theorem say about a graph where all of the degrees are even? There'd be an Euler circuit, right? And if there's an Euler circuit, that's the same thing. An Euler path, well, an Euler circuit is just a special Euler path. An Euler path is the same thing as drawing the graph with without lifting your pen. Uh, Euler circuit exists because of even degrees. Implies you can draw it. Okay, and you can even go through and try to do it at this point, and you would see that you could do it, right? So just pick a starting vertex and then just start doing it. Should be easy, right? I'll just trace the outside. Okay. No, that was wrong. Oh, I didn't put a vertex there. Hold on. I missed one vertex. Blue dot. Blue dot. 4. Okay. Let's try again. All right. So we went there, there. Oops, that's not what I want. There, 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 there. Now, I need to actually finish up here because I left here. This needs to be the last place I go. So if this needs to be the last place I go, I should take a turn here, and maybe I'll do it in a different color. Oops, a different color. So we'll turn this way and go around the center and then end up there. So yeah, you could do it. It's a little bit, tricky to figure out, but you could do it. Maybe it's not tricky. I don't know. It was tricky for me. It took 2 tries. Okay. So anyway, the point is that if you're just trying to draw it, you might not be able to figure it out. But if you look at the degrees, that's actually really fast to just add these vertices and then look at the degrees. And so you'll have this on the homework and probably on your test. You have 1 test left, and this type of problem will be on there. All right, so now that's definitely it for right now. I will talk to you guys later. Yeah, that's about it.